safe to start. Okay, so this is talk on .NET collections. I will just start with the obligatory sort of through my bit, a little bit of self-promotion. I'm Simon Robinson, obviously, blog@takeysimon.com. I have been a .NET developer since a year or two actually before .NET was released. I was a C++ developer in the 90s, and at the point when I was writing books, I kind of got supplied with our early alpha of .NET, like about a year before it was out. And at that point, it was like crashing every 5 minutes. And even so, it was like, wow, I can be so much more productive in this. So I converted to C# and have never looked back. I've got a couple of blog site courses up, including C# Collections Fundamentals, which is due out probably in about a week's time, which sounds like really good planning, but it's actually a complete coincidence. And that actually will cover some of the same material that I'm going to go over in this talk, but in a bit more detail, because I've only got 1.5 hours, and that course is 5 hours, which gives you some idea of the complexity of collections. So, the point of this talk really is, because collections is quite a deep topic, there is loads to learn, but it's something most people don't really study that much. And what typically happens, I've seen loads of times, is you learn C#, you learn about arrays, because you can't really learn C# without knowing about arrays. At some point after that, you realise that you actually want to add items to collections, which you can't do with arrays. So you learn about list of T. And then at some point after that, you get really adventurous, because you discover that actually you want to be able to access collections using keys. So you learn all about dictionary of T key, T value. And the thing is, once you've got those, you can pretty much do most tasks that you need to do with collections. Your code might not look that pretty. It might not run as efficiently as it would do if you used a more suitable collection. But you can get away with just knowing those. And because of that, a lot of people do end up just knowing those. But those aren't the only collections Microsoft have written by quite a long way. And all these other ones, Microsoft didn't write just for the hell of it. They wrote because they actually are useful. There's a lot of situations where these are much better choices than your standard list of T or dictionary T key, T value. So the point of this talk really is to get you from the point where you know about collections a little bit, you've used a couple of collections, to the point where you're like what I like to call a power collections developer, where you've got a much better understanding of what makes collections tick inside, how a lot of them work, and you've got a bit more knowledge of the range of collections that Microsoft offers, and also some of the interfaces, which is also quite important. I'm assuming that you've used collections at least a little bit, and although it's .NET collections, the examples are going to be in C#, so I'm assuming you can read C#, even if you like coding in VB, another language. So in terms of what we're going to do, I'm going to start off at very basics and make sure we're agreed on what a collection actually is. Then, before we look at any types, I'm going to have a look at the collections interfaces. The reason for that is twofold. One is that you do actually need interfaces if you want to write loosely coupled code. And the other is that the collections interfaces do actually give quite a good idea of the structure of collections, of how collections are categorized. And if you understand that, you kind of understand immediately a bit more of how Microsoft intends collections to be used. So I'll start off with that, which unfortunately means not much coding for the first half hour. It's going to be quite conceptual. But then we get to play with some actual collection types. There's broadly 3 categories of collections: lists, dictionaries, and sets. And we're going to go through all those. At the end of that, I'm hoping we'll have some time to talk about enumerators, and then look at the concurrent and immutable collections. Having said that, when I went through this a couple of days ago, I realised there's probably about 2.5 to 3 hours of material there. And I don't think DevWeek will thank me if I carry on until 5 o'clock. I don't want to rush through things, because then like half of you will end up not understanding anything. So I'm going to take things gradually and get as far as we can. And I'll apologise in advance if we don't get onto everything on that list. So, what is a collection? And the way I like to think of it, is it's something responsible for managing items in memory. So this, for example, is a book. A very nice book, actually, when you would do. This whole thing is a collection of books. And a collection is the type that is responsible for providing access to the objects it contains. I also put in memory on that slide, and I think that is important because part of the thing about collections is you have got immediate access to all the things a collection holds. And as a counterexample, we have a link query here. Fairly obvious what it does, grabs some employees from some table in a database. And what it returns is something that you often think of that you do collection type things with, but it's probably not a collection. It's just something that gives you items one at a time. They're probably not all in memory at the same time. It might, depending how that particular query works under the hood, it might be just grabbing a few of them. But on the other hand, if you know link, you know that you can just stick a to list on the end of that, and what you end up with is a collection. So what we're looking at in this talk is the collections after you've got the to list. I'm not going to talk about link much, although because you can do link on almost any collection, it kind of is inevitably going to come up a little bit. So once you've agreed on that, let's look at what a collection, just in purely conceptual terms, what a collection would do. In fact, any offers for what sort of responsibilities a collection should have? Very good one, yeah. Show you some of the items. In fact, just coincidentally, that was the next bit on the slide. And I'd love to pretend that was arranged in advance, but sadly it wasn't. So yeah, the first thing a collection will let you do is look up the items in it. And there are broadly two ways that can happen. Looking up an element or enumerating them. Looking up an element is where you actually go to the collection. You say, I've got some information that identifies this item. Please give me the red book. Well, one that's just red, not red and black. And the collection will serve up that item. Enumerating the elements, which you normally do in a for each loop, is where you just say to a collection, don't give me a particular thing, give me everything one at a time. So enumerating is normally for each loop. Looking up an element for just about all collections is square brackets in C# using an indexer, or round brackets if you use VB. The key difference between those is that enumerating items, that's supported by just about every collection. I stand to be corrected, but I can't think offhand of a single Microsoft collection that doesn't support enumerating items. I'm not quite sure what user collection that didn't let you do that would be. Looking up items isn't universal. There's lots of collections that don't let you do that. Hashtag is one, linked list won't let you do that, stacking queue won't let you either. So that's covered reading from the collection. Next thing, writing to the collection. And there are pretty much 4 different basic ways you can write to a collection. You can add or remove an element, insert or replace it. And the difference between adding and inserting, it's important to bear in mind, when you add an element, you're just basically saying to the collection, take this in, keep this in your collection. You're not bothered about how the collection does it or where the collection puts it. If you insert an element, you're saying, take this item and put it in a particular spot. Put a book on the top, particularly on the top of the pile or as a second item. And the difference between that is adding an item means you don't need to know anything about the collection other than that it is a collection. Inserting something you can't really do unless you know a bit more about the collection. For example, if it's a list, numbers are ordered in sequence, you can say, put this in at the second item, move everything else up. Not all collections will do that. And replacing an element I put in, that's logically, it looks like it ought to be equivalent to removing an element, then adding an element. But it's often a lot quicker than that, because if you remove an element, quite often you need to move other items in memory around. Replacing an element, you don't need to do that. It's just slot one element in where something else was. So I'll take a bit of time to go over that because it looks fairly basic, but that's something to bear in mind with collections. Pretty much every collection, those are the basic operations. When you are choosing a particular collection to use in a particular situation, a lot of the choice comes down to which of those operations does the collection support, which ones are good for performance, are there any issues with any of them? And there's a lot of other things you can do with collections. You can filter items, you can reorder items, but those really are the basics. Everything else you do pretty much comes down to a combination of one of those. So that's just about it for the conceptual stuff. Let's now go on to the actual interfaces. And these are most of the Microsoft Collection interfaces. Not quite all of them, but most of them. And this is probably also the part where you can tell who the real programmers are. If you look at the guy sitting next to you, he's like looking at the guy, wow, interface heaven, then you know it's like a real programmer next to you. If the guy sitting next to you is nervously looking at the door, thinking, how can I escape before these slides get any worse? Then you know it's like probably just an ordinary human being. But it's not actually quite as bad as it looks. We start off with the ones in the top right. Those ones. Those are collection-related interfaces, but collections don't need to implement those. Those are things that enumerators implement. So we won't worry about those for now. And then if you look at what's left, you might notice there's a pattern that there are basically 3 different hierarchies that all 3 of them look pretty similar. You've actually, to some approximation, got the same thing repeated 3 times. So what I'm going to do is I'm just going to focus on the one in the middle, and we'll understand that, and then we'll quickly show how that's related to the other 2 branches of the interface hierarchy. So what we start off with is IEnumerable of T, and that, I'm sure you've all encountered it before, basically says I can be enumerated. If you implement IEnumerable of T, you have a supply of objects that you can serve up one by one. And that doesn't sound much, but it is powerful. It's the thing that Link hangs off of. It's important because if you can enumerate the items in a collection, you can pretty much know everything about that collection. It might take you a long time to do it. If you want to know how many there are, you've got to count them all by enumerating them all. But you can find out everything that's in it. Moving on from that, you then get iCollection of T, and that really is the thing that says I am a collection. It's not the same as IEnumerable, because if you look at think about the link example I showed you earlier, a collection has everything in memory. You can access anything immediately, pretty much. IEnumerable doesn't necessarily let you do that. And that shows up a bit if you actually look at the methods that are exposed by iCollection of T. There's quite a lot of them, but luckily we don't need to know in detail. The really important one is this one on the left here, which is the count property. And that's an important distinction. If something is a collection, it knows up front how many items are in it. Something that's an enumerable doesn't necessarily know that. And I would say that's probably the really important difference between an enumerable and a collection. Beyond that, we've got the contains method and copy to, which are sometimes useful. To some extent, they've been obsoleted by Link. And we have various methods to modify the collection, to add or remove items, and an is-read-only property, which I'll talk about in a minute. So that's kind of, as an interface, that kind of represents Microsoft's original vision of what a collection would be. But what it doesn't tell you is anything about the collection. If you implement iCollection, all you're saying is that you are a collection of some description. Where it gets interesting is when you look at what inherits from iCollection, and that's iList of T, a dictionary of T value, and I set a T. And that's important because those are the three main types of collection that Microsoft offers. Yeah, when I showed you all those collection types earlier, pretty much every one of those types is either a list or a dictionary or a set. So iList of T basically, I won't show you the methods in detail, but iList has an indexer that lets you look up something by index. It lets you say what's the first item or what's the second item. iDictionary, as I'm sure you're aware, lets you look up things using a key. And iSet is a bit different, so I'll cover that in a minute. So that's kind of the central. Oh yeah, I was jumping ahead of myself on the slides. That's the slide I should have shown moments ago, showing everything is either a list, dictionary, or set. And yeah, so the actual difference, a list orders things by index. The other thing that's often useful about a list is they are probably the fastest collections when it comes to looking stuff up. Yeah, I'm sure a lot of the times you've used like list of T or array, and you don't really care about the fact that there's an index there. You just care about the fact that that's the fastest way to get an item out of the collection. Dictionaries give you access using a key. You'll often hear the term hash table, which a hash table is the underlying technology that dictionaries often use. Dictionary of T value underneath it has a hash table. Not every dictionary does. A lot of the other dictionaries don't. Sets are slightly different. Sets gives you no direct element access. Or if you want the elements in a set, the only way you can do it is enumerate them. But what's important about a set is it guarantees uniqueness. If you have a set, the archetype of the set is class #70, then you can't put any element in the set more than once. And they're also quite useful because you can do set operations on them. For example, if you've got two sets, you can say, do they contain exactly the same elements? Which you can do with lists as well, but it takes a bit of work. Sets will do that out of the box. So that's the main interface hierarchy. And these are the ones that you probably encounter the most often. And the other two are there partly for historical reasons. The one on the left arises from the early history of .NET. So if you look at how .NET evolved, it was first released in 2002, but generics didn't arrive until .NET 2.0 in 2005, which was a bit awkward in the early years because every collection requires generics normally. You don't instantiate a list, you instantiate a list of something. So what happened was, before you had generics, you just had the interfaces on the left, which didn't use generics. When .2.0 came out, those pretty much became obsolete. And it would be nice if we could then just forget about them, but we can't, because IEnumerable of T inherits from IEnumerable. That was done for backwards compatibility, but it means we have at least one old interface baked in forevermore, because the contract of an interface says you can't change it once it's out there. The third set, read-only collections, that also comes from a bit of history, which is that, if I go back to the definition of iCollection of T, what happened was iCollection of T lets you modify a collection. It's got these add, remove, and clear methods. And it also has an isReadOnly method. And the idea, isReadOnly property. And the idea of isReadOnly is that if you actually can't modify the collection, you can check that property, and if that returns true, then you shouldn't call the add or remove or clear methods. And that's not really a very nice way of exposing collections as read-only. And Microsoft kind of rather belatedly realized their mistake a few years ago. And when .NET 4.5 came out, they released these read-only interfaces, which pretty much duplicate the core generic interfaces, except they expose no methods to write to them. So they are really good methods if you do want to expose a collection and you don't want someone to write to it. But they do suffer a bit from the fact that they've been added on as an afterthought. I mean, if you were designing this up front, you would probably have iCollection inherit from my read-only collection, because it exposes all the same methods and a few others. But because my read-only collection didn't exist at the time, it doesn't. You ended up with this sort of mess of two parallel trees, which is a bit unfortunate, but it's what we've got to work with in collections. That's it. The other bit of history that's worth noting is that Link arrived after generics, and that's why some of the interfaces now have methods that are a bit obsolete. They've been superseded by Link, but because Link didn't exist when those interfaces were created, again, we're stuck with them. Also, more recently, Microsoft released the concurrent AnyMusical collections, which kind of form another separate set of tags. So that's, I apologise for probably boring you with all that conceptual stuff. Now we are actually in a position to start looking at some types. So I'm going to start off with the lists. There are basically 8 list types that are worth knowing about. The 5 on the left, array, list of T, read-only collection, collection and observable collection, are slightly different from the ones on the right, in that all of these store their items using an index. All of these are pretty much based on that there's a first item in the collection, then a second item, then a third item. But linked list, queue and stack don't actually expose that. So they kind of are lists, but they don't actually, even though they're lists, they won't let you access an item by index, whereas the ones on the left do. That's not much of a restriction because these are designed for situations where you don't need index access. So let's start off with array. An array is an archetypal list, and if we look at it by comparison with the functionality that I've just said all collections should expose, it's a list, but it doesn't let you add or remove or insert an element. It's a fixed size. And that, if you think about it, is a bit weird, because how often do you need a collection that you can replace items in it, but you can't add items to it? It's not that often. And when I was trying to think of a good example of a good use for an array, I struggled a bit and I came up with, you all know the 7 wonders of the world, and as we're in London, I thought we'd have an array of the 7 wonders of London. So you definitely don't want to add anything to it or remove anything from it, because then it wouldn't be 7 wonders anymore, which would be a bit silly. But you might argue about which wonders are there, so you might want to replace an item. To start off with, actually hang on, sorry. I just realised I've been talking this and that's been showing the slide and my computer's showing the code. Let's just try and figure out what the problem is. So that looks like the only way I can stop it showing the slides is by clicking that. That's going to be very useful when I've got to swap between slides and code. Okay, that's the code. So up here are my proposed 7 wonders of London. I started off by going for Big Ben, St Paul's Cathedral, Buckingham Palace, Tower Bridge, DevWeek, obviously one of the biggest wonders, St Pancras Station and chocolate ice cream. All the wonderful things you can enjoy in London. And as a standard list, you can run a for each loop on it. For each works on every collection for enumerating the elements. Let's just prove it works. So run that. obviously as a collection. I should say, is that font big enough, by the way? Can you all see at the back? You can also use the indexer, so if I want to say, get the second element, I can just use the indexer to do that. Everything in .NET, as you know, is zero-based indexing, so 1 means the second element, not the first one. So that would work. That should give me the second element as well as the list. Yeah. And of course, you can also replace items by putting the indexer on the left. So I've said wonders. Come on. Which wonder don't we like? Which one do we want to get rid of? Buckingham Palace. Oh, you rebel. Which one's Buckingham Palace? I'll make that number 2. What do you want to replace it with?
Number 9.
Oh, very good choice. I like that. Fucking type. There's nothing new there. That's most of the documentation would say that is setting an element. I tend to think if you think of that as replacing the element, it's a much better description of what's actually going on. Of course, the Bulls Cathedrals twice because I've still got the first console to write that in. So none of that should surprise you. The key thing about that is just about whatever is in there will work for any collection that supports element lookup. But of course, arrays don't support adding. So if I wanted to say wonders.add, another wonder.
Gherkin.
So,
Gherkin.
Westminster Cathedral. Still on. And run that. And of course, it doesn't build because array doesn't have an add method. Which, if you think about it, is a bit odd because arrays implement iListOfT, and iListOfT derives from iCollectionOfT, and iCollectionOfT definitely does have an add method. So what's going on is there is an add method on arrays, but it's implemented explicitly. You all know what explicit implementation? It's basically if you have an interface, you can only call the method if you actually cast that interface. So I could cast that to an iListOfT and be able to call the add method, and it would probably throw an exception. And that's something else. You know, it sounds obvious, but that's actually another characteristic of collections. You've got this interface iCollectionOfT, which says I am a collection, and you've actually got quite a lot of the actual collection types, which kind of say, actually, I don't really want to be a collectionOfT, not all your methods are appropriate. So you do find a lot of collectionOfT methods get implemented explicitly on quite a few collections. But I'm slightly digressing there. We've established that arrays are strange because they expose a combination of functionality that you don't really normally want. And the question is, why would Microsoft do that? And the answer is, if I can go back to the slides. The arrays are slightly unusual in that they are driven, the methods they expose is driven not so much by what code would need, but what the restrictions of the technology are. And if you look at how an array works, I couldn't be bothered to put all the 7 ones of London on this slide, so I've just gone for an array of integers. If you declare that array of 5 integers, one integer requires 4 bytes of memory. What the CLR will do is it will just say, how many bytes of memory do I need for 5 integers? 4 4 times 5 is 20, so it will reserve 20 bytes of memory, and that's where the contents of the array go, one after another in that block of memory. It's a really efficient way of doing it, both for looking up elements, because if you want to get, say, the third element, it's very easy to calculate where it is in memory. And it's also really, really good use of memory, because you don't need to store anything with each element. It's just the value on its own. You don't need any markers to say where it is. You can calculate that. But doing that way, very efficient. But of course, you reserve the block of memory up front. The memory immediately following it is probably going to be used by something else. If it isn't in use when the memory is allocated, it will probably get taken up pretty soon afterwards. So if you want to add something to that, you can't, because the memory immediately following that probably isn't free. And that's why arrays are a fixed size. But they're also, doing it this way is very efficient, and also important because it's something that the CLR does internally. When we start looking at the other collections, every collection we look at is basically written in managed code. Almost every collection, if you dig inside it, you will find there is one or more arrays that are powering it. Every other collection you could write yourself in C#. But arrays are actually implemented inside the .NET framework. If you instantiate an array, there are special intermediate language instructions used to do it. I've had a little poke around with intermediate language. I'm fairly sure if arrays didn't exist, you wouldn't be able to write one that works like that in C#. You just don't have the instructions in managed code to do that, obviously unless you go into unsafe code. So that's why arrays are very fundamental and very important in the scheme of collections. So they've got the fixed size. As you probably know, they've got special C# syntax, the square brackets. One other thing with arrays, if you actually look at the constructor, when you construct an array, there's C#'s really flexible. There's loads of different constructors. But if you go through them, you'll notice every one you have to specify how many elements there are. There's absolutely no way to instantiate an array without giving the size, because the compiler, the .clr wouldn't know otherwise how much memory to allocate. They're very lightweight. But one thing that's perhaps a bit less well known is they have a very rich API. And I'm now going to try and see if I can get back to the code. Blue code on that. And looks like I can't. If I kill the slideshow, I can see the code again. So if I actually just type in array dot and look at IntelliSense, there is actually quite a lot of additional functionality on arrays. You can do binary search on them, you can find elements in them, you can find the index of elements in them. There's even a resize method, but that's a lie, it doesn't resize the array, it just creates another one. And you can sort them. So there's a lot you can do. For some reason that I don't understand, Microsoft chose to implement these all as static methods. So if you type 7wonders dot, or the name of an array variable, and try and find the methods, you just won't find them there. You've got to actually type array dot, call the method and pass the array as the first parameter, which is a slightly strange design decision. But once you know it, it's quite useful to have. So that's it for arrays. Next up, list of T. A list of T is designed pretty much to be identical to an array, except that it adds back this thing that you can add elements to it. So if I take this declaration and change it from string, say there's some wonders, I have to use a slightly different syntax because I don't now have the special C# array syntax. So what I've done is made that. Thank you. Please someone to wait. But one thing I've changed, and everything still works beautifully, except now that add method works as well. So list of T is really good for that. All the stuff, the extra API on arrays, the sorting, the binary searching, list of T does that as well, but with the difference that they're not static methods on list of T. So now that 7 wonders is a list, I can say 7 wonders dot. And mostly I get link methods, but if I remove this using system.link declaration, so now Visual Studio can't see all the link extension methods, and put a dot there again. And now you can see pretty much the same methods that array has as static methods. So list of T is pretty much designed to be an array with a bit of an additional functionality. And the way it works, of course, is if you instantiate a list of T, what you get is something that has got an array inside it. If I go to the slides. So same declaration as before, but now I've instantiated it as a list, not as an array. You get a type which has an array inside it. But what the .NET framework, so what list of T does, is it makes the array bigger than it needs. So you have this count property which tells you how many elements are actually being used, and a capacity which tells you how many are being used plus what extra free space there is. And obviously if you keep adding more elements to it, the array becomes not big enough. The list of T will just discard the array and create a new one, which is very nice. You do take very, very slight performance hit on that because that's partly because there's an extra level of indirection, but also because now you're dealing with a type that is written in managed code. With array, it's implemented inside the CLR, and that means the JIT compiler can be quite aggressive at optimizing stuff. And as an example, where I have that for each loop, as you know, with arrays, every time you look up an element, the array will do a bounds check to make sure you're not looking up something, you're not looking up the 16 elements of an array that's size 8. For an array with that for each loop, that bounds check probably didn't happen because the JIT compiler will be able to look at that, say, analyze the code and say, I can see that this code cannot possibly access an element that's out of bounds. So it can say, okay, leave the bounds check out of that. Arrays, the JIT compiler is pretty aggressive at doing that. Doesn't necessarily do it every situation, but quite often does. List of T, you're now putting a wrap around that. That means the JIT compiler is going to have a much harder time seeing what's going on. And in all likelihood, those bounds checks now will happen. But you get a lot of flexibility for that. So moving on from list of T, the thing about list of T is it gives you absolute complete control. If you're calling some other method somewhere, and you give it a list of T, that method can do anything to that list. It can add stuff to it, remove elements from it. So that brings up a question. If you're passing a list to some other code and you know you don't want to change it, how do you stop that other code from changing it? And normally there are 3 ways that you might consider doing that. You could try casting, you could try copying, or you could try encapsulating. Casting probably means you'll do something like this. You will take your list and you'll try casting it to a read, say an interface, an I-read-only list, which you know does not expose any methods to modify the list, and hand that to this code that you perhaps don't fully trust. That's not a good solution. Anyone know why? Go on.
Because that's still an I collection. Therefore, you can't see the collection.
Yeah.
Add to it.
Exactly, yeah. So you class that, you think, yeah, you're expressing your intention that you don't want anything to add to the list. There's nothing to stop the code you're passing it to from casting it right back to a list and then doing whatever it wants. And it might not even be deliberate. You could pass that to some code. Inside this other code, it goes through 20 layers of method calls written by some other developer. And then it hits a method where someone in complete innocence wrote some code that says, hang on, let's look at this. Is this a list? Can I actually pass this and do stuff with it? So as a way of protecting your code, that is good for expressing your intentions, but doesn't really give you any real security. Copying, on the other hand, means doing something like this. You call to list, you take a copy of the list, or of any other collection, and you pass that in. And that is completely safe as far as making changes to your list are concerned, assuming the code you're passing it to is at least not using any unsafe code or anything. But it's not necessarily good for performance. If you've got a list of 6 elements, that's fine. If you've got a list of 2 million elements, and you're passing it to some code that only wants to look at a couple of them, that's probably not a good solution. Which leads us to the third one, which is encapsulating. And list.t has quite a nice method to do that, which is a method called asReadOnly. And if I go back to the code, what asReadOnly does is it quite literally it creates a new collection which wraps your existing list, and this new collection basically guards all access to the underlying list and prevents any writing to it. So in this code, number 7 wonders is a list of T. I'll just say asReadOnly. Oops, wrong method. asReadOnly. Store that in a variable. Let's call it safe. asReadOnly. And if I want to do a for each loop on that, I can do that, that's fine. That works perfectly. But if I want to take this safe call up to above where I try and make changes to it, and say safe 2 equals underline, safe.add, it doesn't work. And you can't even compile that. What you're getting from this asReadOnly call just doesn't expose methods to modify the collection. But the thing with asReadOnly, it looks very useful. It's almost a waste of space. It's just a little bit of syntactic sugar, because all it's actually doing is this. Under the hood, asReadOnly is just creating a new thing called a read-only collection and passing the individual collection stats. I'm getting a squiggly red line. The reason for that is that read-only collection is not in system.collections.generic. It's in another namespace called system.collections.objects model. So I'll put that in. That would explain why IntelliSense wasn't working. I'll probably do that, thanks. So with that namespace in there, this should work. It doesn't. And that's going to be because I actually need to tell it it's a read-only collection of string. So the compiler is happy with that. Obviously, it's not happy with the fact that I'm trying to change these to a read-only collection. So let's comment those out.
So that one doesn't do a copy?
It doesn't do a copy, it actually wraps the underlying collection. Which also means you want to watch it because you can't change the collection through the copy But if you've still got a reference to the underlying collection, you can change that. And if you change the underlying collection, the read-only collection will see a change. So that is a good way of actually protecting your list from changes. It's not something like, if you're really worried about security, if someone could use a read-only collection and use reflection to get at the underlying list. But if it's just you want to express your intention and make it difficult for, make it impossible for someone to accidentally modify your collection, that's a great way to do it. So that's making the collections read-only. There's actually another way that you might want to protect collections. As an example, let's suppose you've got a list of string, and suppose you want to guarantee that that string list will not have any null strings in it. Or suppose you want to guarantee, that it will only have lowercase strings in it. Now that's something you can't do with list of T. But if you want to restrict access to a list in that kind of way, there is a collection that will let you do that, and it's called collection of T. And I'm just going to show you that. And the way I'm going to do that, I have a slightly different sample. Just bear with me while I find it. Right, I've changed things around in this, and instead of representing wonders of London by strings, I actually have a type called wonder, which you'll see in a minute as soon as Visual Studio is loaded. Okay. And this is a pretty simple type. All it is, it just stores the name of the wonder and a rating of how wonderful it is. It's got the usual constructor, just to supply the two things, and a two-string method that displays that. And what I'm going to have is I want a collection which guarantees that I will only have fairly good wonders in it. Wonders that have got at least a certain rating. And I'm going to say let's have wonders with a rating of 50 in them. So, to start with, here is roughly the code I had before. It's a list of wonders, got a list of strings now. And I've instantiated it with 7 wonders. Big Ben, I think, is worth about 20. What wonderful St. Paul's Cathedral's Thursday, so 30. DevWeek obviously is miles better than almost anything else, so that's 20,000. And chocolate ice cream is just off the scale. I couldn't think of an integer big enough for that. So if I want something that can only store decent wonders, list of T is not really going to help, because I've obviously put in some not very good wonders in that, and I can run that code, and everything's happy. And obviously, I could put a wrapper around that. I could put some code to guard against it, and everywhere where I store something in the list of T. But that's not a very robust solution. So what I have instead is a new class called Top Wonders List. And what I'm going to do is I'm going to derive that from a class called Collection of String. And the compiler is not happy because, just like read-only collection, this is in system.collections.object model. So let's stick that namespace in. And the compiler should be happy with that. Yeah. So, collection is very much like read-only collection. It provides a wrapper around some underlying collection. But where collection is designed to make it read-only, so where read-only collection is designed to make it read-only, collection of T is designed to let you put any custom behavior you want. So what I'm going to do is I'm going to type in override in the space and see what that gives me. And it gives me several methods that I can override to control the behavior. And if I want to make sure that I can only put wonders that are reasonably wonderful in that, the methods I want to look at are insert item and set item, because those are the two things that happen if something is added to the list. The way it works is that there are several ways that a collection will let you add something to the collection. For a list, you've got the indexer, you've got an add method, you've also got the sort of obsolete .NET 1.x add methods. But every time you try and add something to the list, it will either come down to it will either internally call insert item or set item. So if I override both of those methods, I can control all adding items to the list. So I've just let Visual Studio give me an implementation of insert item. Base.insert item actually inserts the item into the list. So all I just want to do now is say if the
exception of one.
yeah. No, I've done something wrong there.
At the wrong time.
Yeah. Good point. Which one there? So, insert item. I'm not really interested in the index. What I'm interested in is the item. And I just want to say if item dot rating, say less than 50, then throw me the exception with some suitably angry exception message. Obviously, in your code, you would probably put something a little bit more explanatory as an exception message. And then I just want to do the same thing for set item. And that's it. I now have a list that will reject any wonders with a rating less than 50. So if I change this list of wonder now to a new top wonders list, and on that, we are expecting that this code will fail because I'm adding several not very good wonders to it. So if I run that, and yet, unhandled exception. Windows is checking for solutions to the problem. No, I don't really want to tell Microsoft what the problem is. And somewhere in the exception message should be the bad wonder. So if I comment out the two wonders that are less than 50 and how wonderful they are, okay, everything else is at least 50, especially the chocolate ice cream, and that's fine. So if you want a list that you can customize, that is the way to do it. And if I just go back to these slides again. Control. That's what I wanted. So basically, if you want something, so arrays and lists are great if it's like tightly coupled code, if you want full control of them, and or if you want to access all the additional functionality that they offer. Collection and read-only collection are the ones you want if you actually want some sort of protection or you want to customize behavior. The naming is a bit screwed up here because collection and read-only collection are both lists. They are more than collections. Microsoft, I have to say, they have given us a really great set of collection classes. Their naming of the collection classes is not quite so brilliant. So that's collection and read-only collection.
So,
Sorry, yeah.
what's the advantage of deriving from collection there rather than list? You could derive from list and override the methods, the equivalent methods.
List doesn't have any methods you can override.
Oh.
One of those, when I overrode those two methods in collection of T, I could do that because they were virtual. List of T is designed to be really lightweight, no virtual methods. One of the, while we're on the subject of customizing behavior, sure. How many of you have used observable collection of T? Those of you. How many of you have used observable collection not in a WPF project? Maybe, a couple of you, yeah. Yeah. It's a common misconception. Everyone thinks of observable collection as a WPF type. It's not. It is a list that basically, if you make a change to it, it raises events, so you know if anything's changed. It's there partly because Microsoft needed it for WPF, but it's not a WPF type. You can use it in any project. And the particular thing I wanted to show you about it is this is a bit from the MSDN documentation. Look at the inheritance bit. We have observable collection derived from collectionality. So Microsoft have implemented observable collection in exactly the same way that I've just implemented that top wonders collection, which I think is quite a good mark of how useful collectionality is if Microsoft use it themselves. So those are pretty much all the lists that give you direct element access. I'll just very quickly run through the 3 lists that don't give you direct element access. I can see time starting to run a bit short, so I'm not going to spend that long on these. We'll start with the links list. You remember with array, everything in an array was stored in memory in one single block. And that's really good for looking up items, but it's rubbish if you want to make modifications, not to array, but to a list. Because if everything's in one block, you may need to move items around in memory. Linked list works a bit differently. The way a linked list works is you have first item. First item stores a pointer to where the next item in memory is. And that stores a pointer for the third item, and so on. So if you have the first item, you can tell what the second item is, you can tell what the third item is from that, and so on. Now what this means with the linked list is you can't jump to an element. If I ask the linked list for the 6th element, the only way the linked list can do it is by going through all the first 5 elements to find it. So you don't really want to do index lookup on that. Enumerating is great because enumerating, you just go through the elements as normal. So performance on that is pretty good. And modifications are really good because, say I want to insert something between the first item and the second item, all I have to do is get the next item, change my next pointers here to point to the new item I'm inserting. On the new item, get its next pointer, change that to point to the next item in the list, and that's it. So linked lists are lists that are great if you need to add and remove elements a lot. They will really help your performance with that. In .NET, they are slightly more complicated. What happens is you store a previous reference as well as the next reference, and that means you can enumerate through the list backwards as well as forwards. There is one obvious disadvantage with that, is notice each item you've got to store a previous pointer and a next pointer, and that means they are pretty inefficient in terms of memory. every element in the list, if you've got 2 million elements, you've got 2 million previous references, 2 million next references. And in fact, what happens is this whole thing is wrapped up in a class called a linked list node, which means you've also got another reference. And the linked list node also stores a reference to the containing list. So you've got a pretty big memory hit. And I will very, very quickly link this code. And I've got the slides still up there again. Actually, I won't do that. Because it's so difficult to swap between slides and code, I'll leave the slide up there and just quickly show you stack and queue, and then quickly jump to the code. So the stack is for a situation where you want the first in, last out collection. Classic example is if you think of the call stack in your code, you call a method, that calls another method. Each time you call a method, something gets added to the call stack. The only thing you can remove from the call stack is the method you just called. The only method you can exit from is the one you just called. So what that means is if you've got a stack, you can add or remove items at the top of it. That's known as pushing an item. And if you want to get an item from the stack, you can't ask the stack for a particular item. The only item you can ask for is the one the stack tells you can have, which is the one on the top. That's the first in, last out collection. Queues are pretty similar, but the difference is that you remove an item at the opposite end from where you added an item. So the name is pretty intuitive. They work exactly like an everyday life queue. You enqueue an item, and then you dequeue it off the opposite end. And the code for all of those is actually very simple. Close this window so you can see the code again. So close that and open. Link list. Linked list of these is probably the most complicated to use in code. And the reason for that is because you don't just have the linked list, you have this other type, the linked list node, that represents the individual elements. So I've still got the wonder type as the thing I'm storing. And, okay, looks like I've actually set this example up as a stack. Okay, we'll show you stack first. So you just declare it as a stack of the given type. Stacks and queues and linked lists don't let you set elements in an initializer. So if I want to get the wonders on there, I have to do it in separate calls to push. And it's very simple. I just, each one I put on, I just push it onto the stack. And the for each loop, remember, works on any collection, so it will work for a stack. So if I run that, there it is. Notice the for each has it enumerated the elements in reverse order. So it's giving you the elements in the order that you would get them if you pop them off the stack, not the order that you push them on. And if I do actually want to get something, well, I just...
For each push, does it pop them? Or does it just when you do it for each?
No, it doesn't pop them. It gives you them. In fact, I can prove that because what I'll do is I was going to show you popping an item, but I'll do it after the for each loop. So if for each pops them, there will be nothing there. So I say one does not pop. And you don't need to pass anything to it because You don't get any choice which one do you get. The stack will control that. So there, I'll call it last equal one. So after the for each loop, that should give me the thing I pushed on it last, which would be chocolate ice cream. And yeah. So it's a bit hard to see because I didn't put an extra line there. But that's all from the for each loop. This is from popping the item and then displaying its value. Q works pretty much the same way. So if I change this to Q, it does. But Q, you don't push an item, you enqueue an item. So if I just change, take every console push to enqueue, now we'll be happy. But it's not going to be happy about this pop, because you don't pop an item off the queue, you dequeue it. And that output should be exactly the same, except that for each has again given you, is enumerated the items in the order that you would get them if you dequeued, but that's now the order that you put them on the queue. So that will have to be reversed. If I want to make that a linked list, I'll just again change this to linked list of wonder. And you don't enqueue to a linked list. You've actually got a few add methods here. If I just use IntelliSense, you've got add after, add before, add first, and add last. And those basically control where you want to add something. If I just say add last to all of those, and that will put them on the linked list in the same order. And of course, the linked list has no concept of dequeuing. Oh, what have I done wrong?
Gone now to find last. Tangling now.
Good point. Yep, so just enumerating. Now with a linked list, when you actually add something, you actually get return. When you add something, I've added a wonder to a linked list. Now a linked list, remember, has basically got a set of linked list nodes. It hasn't directly got the wonders in it. But what happens is when you call that add last method, it returns, it creates the linked list node and then returns it. So if I say there last equals wonders.add last, and now I can uncomment my console.writeline again, and run that. And of course what we see is that linked list node doesn't have a nice toString overridden on it. So if you want to actually see what's in it, I've actually got to say last dot value. And that will work. Now with a linked list, storing these actual, if you add something, if you think you are going to want to add something after or before it later on, you need to store the reference to that linked list node. Because if you don't store the reference to the linked list node and then you want to add something before or after it, the linked list has got to find the node, and that means it's got to go through the whole linked list. So they are a bit more complicated to use than normal lists, but well worth it if you're going to be adding and removing items a lot. So that's it for lists. Let's quickly look at dictionaries now. So what I'm going to do, is that project. And I have, surprise, a dictionary of wonders of London, which of course you weren't expecting at all. Now, dictionary is conceptually a bit different from lists because you have to store something by a key. So what I've done is I have changed my definition of wonder a little bit. As well as the name and the rating, I now have an ID for it. And the ID is going to be the string that I use to look it up. And the two strings changed a bit, so it displays all three items. And in the main program, I have my main method. I couldn't be bothered to write all 7 wonders as dictionary items, so I just got 3 of them. And then I set a 4th one using the indexer syntax. And that's a feature of dictionaries. You can use the indexer either to replace an item or to set an item if it wasn't already in the dictionary. And then I have a console.write line just to look up one of the wonders. I've gone for the one with the key TB, which is Tower Bridge. And then for each to write them all out. And that works fine. Now, that's also really, really efficient. And I should probably just show you quickly how that works. What's happening is that under the hood, it looks like under the hood I've lost the PowerPoint presentation. Oh yeah, actually something I should point out. When I run that for each loop, notice what has got printed out. I started off with the first element. I said the thing with key was Tower Bridge. When I enumerated them, I got key, comma, value, all in square brackets. And the reason for that is because conceptually a dictionary is not a collection of its values. Conceptually, a dictionary is a collection of what are called key-value pairs. And that's basically a symbol type that encapsulates both the key and the value. And Microsoft did a slightly better job with that than they did with linked list node, because they've overridden the string to actually display something sensible. So, this one just shows how dictionary is actually set of key-value pairs. Now this one, more interesting, is how a dictionary actually works. And what happens is every object in .NET exposes a method called getHashCode, which basically produces a hash of the value of the object. A hash is basically just a 32-bit number, which hopefully, if objects have different values, they will tend to give different hashes. And what a dictionary does is it has a number of buckets. If I say I want to add DevWeek to this dictionary, what happens is it does a little algorithm, basically does a modulo of a hash code per number of buckets, and that tells it the buckets are at the beginning. And notice that sometimes things will go in the same buckets as other items. If I then want to look up, say, DevWeek, the dictionary passes it into the same algorithm. That tells it which bucket it's going to be in. But unfortunately, it's then got to search through that bucket to find it. So that's conceptually not too bad. What the buckets are internally is linked lists. which means if you want to add something to the dictionary, it's fairly good once it's got to the bucket, because adding and removing to a linked list is quite quick. But what it also means is you do need to be careful with the hash code. And I'm just going to show you that's the code. Right. Let's say when I'm looking up DevWeek, I don't really care about the case. So I part, actually that's not looking up, that's when I'm setting it. Let's go to when I'm actually looking up Tower Bridge, I do it with the lowercase. And it's sort of obvious to you and I that I want a thing with key TV. But of course, if I run it, I get an unhandled exception. Because as far as the .NET framework is concerned, uppercase and lowercase TV are different strings. If I want to fix that, I need to tell the dictionary to use a different way of comparing the keys. So, what I'm going to do, you can actually pass the comparer to the dictionary's constructor. And in this case, I want something that compares strings, ignoring the case. And rather nicely, Microsoft have actually written that for you. There's a class called string comparer, and it exposes lots of different comparers. So that's can't culture ignore case, that looks good enough. So if I run that, everything is fine again. But suppose that didn't exist. Suppose you were in a situation where you did actually need to write your own comparer. Well, what this comparer is expecting is something that implements an interface called iEquality comparer. So let's just pretend, for some reason I can't use the string comparer one. I want to write my own one. So let's do a class under key comparer. And I need that to implement iEquality comparer of string, because the keys are strings. And I want squiggly braces, not square brackets. And let's get Visual Studio to implement that for me. Interface. And it's given us two methods to implement. First one, an equals. That's pretty easy. If I want to compare strings and ignore the case, I think. That should do the trick, shouldn't it? Good. Spotted my deliberate mistake again. Full marks. Especially when it's that time on a Thursday when it's afternoon nap time. What do we do with this get hash code? Well, as a first approximation, we could think Microsoft have done a pretty good job of writing hash codes for all their types. If we want a hash code of a string, let's just get the hash code of the string. Get hash code. And that is a good principle with hash codes. I need a return. My fingers don't like typing return. There we go. Now it's happy. General thing with hash codes, don't implement them yourself if you can avoid it. Use what Microsoft have done for you. Much easier. So if we do this, is this going to work, do you think? No. Why not? Very good, yeah. You don't want to be in this talk. This talk's too easy for you. Yeah, if I run that, The reason it works is because it's still using Microsoft's string comparer, not my one. Now if I put, and I need to new that. Now if I run that, now it's not going to work. And the point there is, of course, the equals works fine, but uppercase TB and lowercase tb have probably got different hash codes. So when I try and look up with lowercase tb, the dictionary will follow the lowercase tb's hash code. It will end up in the wrong bucket. It will search the wrong bucket, obviously won't find the value it's looking for, and throw the exception. So what I want to make sure is that the hash codes always, if two objects are equal, they give the same hash code. And the easiest way to do that, in this case, is just convert to uppercase and get the hash code of that. And now it's all happy. That's a bit of use of dictionaries. Now, dictionary isn't the only type of dictionary. I'm going to comment out my custom comparer. I'm going to put this back to uppercase, so all words. And there are two other useful dictionary types. One of them, I'll just change the dictionary to vast. Instead of dictionary of string wonder, I will just say sorted list of string wonder. And what's that? And it works exactly the same as before, but when I enumerated the items, you notice they are now in alphabetical order by their keys. And as far as you're concerned, if you're using a dictionary, that is the only difference between a dictionary and a sorted list. They are both dictionaries, but dictionary TPT value doesn't bother to return elements in any particular order. Sorted list does. And notice is another great example of Microsoft naming, where we've had collection of T, which is actually a list, and now we have sorted list of TPT value, which is not a list at all, it's a dictionary.
Does it derive from our dictionary?
It does, yes. And you also have another one called sorted dictionary. Any guesses what the difference here is going to be? No? Go. Say that again? No, nothing to do with unique keys. No, I will show you. This is what the difference is. None at all. Right. Basically, if you don't care about sorting, you can use a dictionary. If you do care about sorting, you can use either a sorted list or a sorted dictionary. In terms of what they do, they are completely identical. The difference is that they have different internal implementations, which gives them different performance characteristics. Sorted list is stored as a list. And basically what happens is the list is sorted as you add elements to it. And then whenever you want to find an element, it just does a binary search to find the one you want. And that's really why it's called sorted list, because externally it's a dictionary, but internally it's a list. Sorted dictionary has a sort of complicated tree structure inside, and the difference that makes is sorted dictionary has a bit more overhead to create, but you can add and remove elements quite easily. Sorted list, because it's a list inside, adding and removing elements carries all the performance penalties that the plain list does. If you add an element, you've probably got to move other elements around in memory. So sorted list, great if you want a dictionary and you don't need to add elements to it very often, and you happen to want it sorted.
Excuse me,
Yeah?
with the initial dictionary, what happens when it grows?
Right, generally speaking, as it grows, you just add more items to each bucket. That's quite quick to do because buckets are stored as linked lists.
Does the number of buckets increases? Because
It will increase eventually, yeah. There is some fairly complicated internal stuff in there which tries to keep the number of buckets enough that you don't need to put too many items in any one bucket. It's a very complicated class, this implementation. But yeah, that's how it will happen. So adding items to a dictionary, performance-wise, is fairly good.
Does it have the option of specifying a capacity up front as a like a list?
I don't think so, no. I don't want to say absolutely definite no, but I've not seen any other ways to do it. It's got so many methods, I might have missed something. So I've got 5 minutes left. There's one other thing in dictionaries I want to show you. And I'll just all of the code that it wants to keep. Right. Let's go back and look at this, how I've initialized this dictionary. I've got new wonder supplying the key, the value, and the rating. And I've supplied the key again. That's not really a very robust way of writing code, is it? Putting the same thing in twice. Makes the code complicated, means I've got potential for typos, destroying everything. It would be much nicer if I could just tell the dictionary how to extract the key from the value. And you can't do that with, obviously it only works if you can extract the key from the value, but in this case you can. You can't do that with dictionary of TQT value, but there is a class that will do. And it's another one that's in system.collections. Object model. And anyone know which class I'm thinking of? No. It's keyed collection. No. Oh, let's just go with that. Right, so what I do, I can't directly instantiate a keyed collection. It's an abstract class. You've got to derive from it. So I'm going to say class wonders. Let's call it just wonders dict. And I'm going to derive it from key collection. Key is still a string. The value is still a wonder. And the reason you have to derive from key collection is because you have to tell the class how to extract the key from the item. So if I just do override, is the one I want, get key for item. I don't want to throw an exception on that. I just want to say return item dot ID. And that's it. These days you would probably use a delegate or lambda for that, but this is quite an old class. There weren't lambda expressions at that time. Microsoft decided to do it, so you had to override it. So instead of sorted dictionary, I'll just do keyed collection. I'm conscious we're running out of time, I'll stop as soon as I can after this. And of course, it doesn't like that because I don't want to say new keyed collection, I want to say new the class I derived from it. So I want to stage. And now all this is wrong because keyed collection knows how to extract the key from the value. I don't need to tell it the keys independently. should be happy. Need something.
Yeah, the title.
You've got 2 typewriters
Ah, good point, yeah. Which I don't want because do that. If I comment that it's not going to like it, key collection doesn't let you use the indexes to set items, you've got to use an add method. Other than that, it works pretty much like a dictionary, except that the items are now not key value pairs. Conceptually, it is a dictionary of its values. Key collection is a bit more powerful than that. What it's actually doing is it gives you a couple of other things. It lets you customize its behavior in the same way the collection does. But it also actually stores a list and a dictionary internally. So it's not perhaps so good for adding lots of values. It's got rather a nice feature because dictionary gives you quite a high overhead. And the key collection will actually not instantiate the dictionary until it's got a certain number of items in. So if you've only got a few items, you possibly can use the key collection and get less overhead than a dictionary. And we're pretty much out of time, I'm afraid. We're missing out on sets. I would just say if you want a collection where you can guarantee not being able to store the same item twice, and want the collection to enforce that, look up #17 and sorted 17. And that I will finish there.